to finish up any assignments that we have outstanding. Before 6 is talking about congruence and right triangles. So all this is an additional technique that allows us to prove specific triangles congruent now. So everything that we've done so far, so these tools of side, 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 angle, side, angle, side, angle, and angle, angle, side, those are all allowing us to prove two triangles congruent. And those triangles, they can be of any characteristic, meaning they both could have been isosceles, they both could be equilateral, they both could be right triangles, they both could be scalene, they could be right scalene, whatever, okay? So it doesn't matter the type of triangle that those work in, okay? Today, we're going to talk about a theorem that works only for right triangles. So before you can use today's theorem, you have to first recognize that you have a right triangle. How do we recognize that we have a right triangle? Okay, so if you have a triangle that has a right angle in it, right? Okay, that needs, if we're going to do a proof with these, that would need to be explained in our proof before we use this theorem. And what this theorem is called is hypotenuse leg, so we need to know what are those things. What is the hypotenuse? So what do you guys know the hypotenuse to be? Okay, so it's the side that's opposite your right angle, correct? Okay. It is the side that does not make the right angle. There's another way of thinking about it, okay? What is a feature that you always know about the hypotenuse? How? It's got to be the longest side, okay? The hypotenuse is the longest side. Now, what were you saying? It was shorter than?
Both of the sides, the other sides besides the hypotenuse combined.
Okay, so the hypotenuse is always going to be, so if this side here is 3 and that one's 3, this one is going to be 3 radical 2. Basically what he's saying is that one there is going to be smaller than the other two added together. And that is actually, that's true, and that is actually a fact for all triangles, that the largest side is always smaller than the other two added together. Okay, if that rule is ever violated, and we'll talk about that later on for another day, but if that rule is ever violated, then your triangle does not exist. Okay, but the hypotenuse by itself compared to the other sides is always the longest side. Why has it got to be the longest side? Okay, so it's got to connect that endpoint to that endpoint, right? But why are those endpoints further away? Why are the endpoints with the X's on them further away than maybe the endpoints that have zeros on them or O's on them? Why are these two endpoints here closer together than those two endpoints? What is this angle right here? Now, you can't tell me that it's a number. You don't know the number, but it's acute, meaning that it's smaller than that one, right? What's this angle right here? Acute, meaning it's smaller than that one, right? And haven't we talked about the largest side of a triangle always has to be opposite the largest angle? Okay, so even though I don't know what these are, they can't be 90 or greater, so they got to be less than 90, meaning this has got to be the biggest angle, so opposite it has to be the biggest side. Okay, essentially meaning then that this, because this angle has to open up more, okay, then that distance there has to be greater so that the endpoints can touch. Okay, so that's the hypotenuse. Then the other two sides are referred to as legs. Okay, so what I like to do is I like to identify my hypotenuse, and then by default that means everything else has to be a leg. Okay, you can think about the legs as being the sides that create the right angle, correct? Okay, there will be another term that we identify a leg with for a right triangle. Does anybody know, like if this was, like let's say that this red segment here that I just drew was like the surface of my desk. And I gave you, like, you guys remember doing tanagrams back in like the 6th and 7th grade? You guys know what tanagrams are? these things? All right. If I were to give you one of those, so it's just basically a wooden block that looks like a triangle, right? And if you were to set that up on your desk, does anybody know what they would call this distance right here? Okay, so a lot of you refer to it as height, which we call it in our formula. What's the formula for a triangle's area? 1/2 base times height. Now, that comes from length times width. Okay, so somebody said length times width, and we'll talk about that maybe here in a little bit. When a lot of people say it's 1/2 BH, and they say H to be height, which makes sense, as if this is sitting on my desk, this would be how tall or the height that thing is off my desk, right? If I'm in an air, anybody been in an airplane, like a commercial airplane, and the pilot, once you guys get to like a cruising level, the pilot will come on and say, we are currently flying at 3,000 or at a blank of 3,000 feet. What's the word that they put in front of that? Altitude. Okay. So altitude, which is analogous to height, is what we would call, this is an altitude of that right triangle. For the same reason, this, even though it's not, and this is where the mathematics kind of definition comes into play, that distance is also referred to as an altitude. Okay, but it's not height now that the thing is off the desk, right? Or the height that something is in the air. But if I were to take this tanagram and reposition it, so it's kind of like that, would you guys agree? So this leg here, that leg right there, is now that leg. Does that make sense? Now you could envision that as being a height, correct? Does that make sense? So that's all, and that's all terminology that we'll get back to and discuss later on. You guys said, just because we're talking, but this will be, I mean, there's a whole chapter devoted to area. You guys said the triangle's area was 1/2 BH, right? Somebody said LW. Well, if I go LW, L times W is the area of a rectangle, right? What if I put that line in there right there? Close. Starts with D. No. That's a diagonal. Okay. But what is the area then, if the whole rectangle was length times W, what is the area of that triangle? 1/2 of that, right? So 1/2 of the length times W. So in a rectangle, though, a lot of times, most textbooks in talking about the area of a rectangle, they call this H and they call this B instead of L and W. Okay. Does that make sense? In every single triangle you ever come across. So let's say that I talk about that triangle right there. Okay, that doesn't look like it's half of a rectangle, does it? But if I do this and take that triangle right there and that triangle right there and like slice them off and reposition them, this triangle here would maybe be that one, and this bigger triangle could be made to be that one, which that then would be the same as this red one, right? So you see that this one here, this whole rectangle, would be twice as much as that triangle. So therefore, one triangle is half the rectangle. So every single triangle you come across, the reason its area formula is 1/2 BH is because it's half of the rectangle. Now, getting back to the current concepts, do we all feel comfortable with identifying the hypotenuse in the leg? Okay. So we have what we call the hypotenuse leg theorem. The hypotenuse leg theorem are called the HL theorem. Okay, so all the other ones were side, 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 angle, 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 side. This one's HL. This one's, it's a little bit different. It's different, and it's good that that's different because it reminds us that it has to have a hypotenuse, and that reminds us then it can only happen in a right triangle. Okay, we all agree that not every triangle has a hypotenuse, right? Only right triangles have something called a hypotenuse. All triangles have a longest side, okay, but not all of them is that longest side called a hypotenuse. Here it says if the hypotenuse and the leg of one triangle are congruent to the hypotenuse and the leg of a second triangle, then the triangles are congruent. Okay? So the hypotenuse and a leg. Now let's think about this. Hypotenuse and a leg. So what we're going to look at here is if these are right triangles, so we'll have that identifier there. Okay? So this would be the hypotenuse, right? So let's say that segment is congruent to that segment. And then a leg, it doesn't matter which one we mark here for the sake of this visualization. I'm going to say this leg here and that leg there. Okay? So that would be the markings that we use to determine hypotenuse leg. Okay? Or, like I said, it doesn't matter which legs for this purpose, but we could look at those two legs being congruent. Now here's my question. That's hypotenuse leg, so we know how to be in a right triangle. What is the order of parts that we've marked here? Because what do you know about this angle here compared to that angle there? They're the same. So if I think about the parts here using A's and S's, is the A between the two S's? No. So if I was going to use S's and A's, then it would be that, right? Which we know talking about that backwards was something we shouldn't write, and something that never shows triangles congruent, right? Doesn't guarantee congruence. Okay. So hypotenuse leg is the same thing as side-side angle. But earlier in the week we said side-side angle was not a condition that guarantees congruence. However, side-side angle does guarantee congruence if you're in a right triangle. Does that make sense? So to remove the ambiguity, the confusion, the ability for somebody to say, oh, side-side angle works here because I've got those parts, but it not be a right triangle and it really not be something that should work in that situation, to remove that confusion, we use HL instead, because now the H tells us we got to have a hypotenuse, so we must be working in the right triangle. Does that make sense? So hypotenuse leg and side-side angle are the same ordering of parts, but side-side angle does not guarantee congruence in triangles. So what I want to do is demonstrate to you why side-side angle does not guarantee congruence, but hypotenuse leg does. They all, if we're looking at two triangles like this, so let's say that I've got that triangle there and that triangle there, obviously not right triangles, correct? If I go side, side, and then that angle there congruent to that angle there, I cannot guarantee that those two triangles are congruent. But I can if one of these is a right, if that's a right angle there, and that's a right angle, now I can guarantee that they're congruent. Let me... Say again? That's the only time that you can use side-side angle. And instead of using side-side angle, so we don't get confusion that we can use it all the time, we rename it or relabel it as hypotenuse leg. So let me show you, and it might take a minute for me to dig this out of my files, but we'll kind of visualize this version of this somewhere, but this will make do. Right now what I've got here is this setup where I've created a side here, okay, and a side here, and then my angle. So I'm side-side angle. Does that make sense? Okay. Now with side-side angle, the way this is set up, if I start to, so right now this does not make a triangle. It's only going to make a triangle once I connect this red dot here with this line right here, because that line, so if I got a 45-degree angle right there, that side of that angle is dictating the third side of my triangle, correct? Does that make sense to everybody? And now when I move this down, my third side of my triangle, the length of it is now going to be from there to there. Does that make sense? So that's why I was making that dotted, because it really doesn't exist in its entirety until this gets to there, okay? But if I do that there and I do that there, okay, would you agree that those two triangles are congruent? Okay. Head shaking yes. Okay, so let's do this. Let's manipulate these sizes a little bit. Let's go 5.9 and see if this one goes down to 5.9. Come on. There we go. Would you guys agree? So if I do that, so that would be a triangle there, correct? And those would you agree we can put those on top of each other and be congruent? Okay. Do you see that triangle? Do you see, so we've got, right now we've got ultimately that triangle there, and now over here, I've got that triangle. When I look at this angle right here, where my cursor is, that's 45 degrees, just like that angle there was, right? Okay. I've got two sides of this little triangle over here that are 6.5 and 5.9. So I've got an angle, a side, and a side, congruent to an angle, a side, and a side. But are those two triangles congruent triangles? No, they don't overlap each other, right? They're not cut and paste one another. So there, even though we have angle, side, side, okay, it does not guarantee congruence, okay, because those two triangles are not congruent to one another, okay. Now, so basically what happens here is that we could have that triangle, when we have certain dimensions of that third side, and it's essentially this 5.9 side that is causing the issue, in comparison to ultimately this, what we call an altitude here in the middle of this triangle. What happens is I can when I swing this third side around, I can intersect this ray that is being made by that 45-degree angle, either there one time or there another time, okay? If we were to kind of trace that, okay, get the circle, right? Basically the idea is if this circle is to intersect this segment down here 2 times, or this ray down here 2 times, then you cannot guarantee congruence, okay? Some distances of that third side won't even let me create a third triangle, okay? Because if you would trace that circle out, it doesn't even come in contact down here. Does that make sense? Okay, so if this is my third side, this second side never touches it to create the third vertex. So when this little arc here intersects that twice, we could have 2 triangles. When this distance here is 4.6, let's look at tracing that distance. How many times does this circle touch that dotted line now? Just touches it once, right? Does that make sense? And if that touches just one time, oh, I don't want to trace it anymore. Right there, okay, what kind of triangle do we have here? That's going to be a right triangle, okay? And if this is 4.6 over here then, and we do that, okay, oh, 4.6. Again, we now get this triangle to be a right triangle and that to be a right triangle. Does that make sense? So if it's a right triangle, would you agree that they are congruent now? So side-side angle, if working in non-right triangles, it doesn't guarantee the triangles to be congruent. But if working in right triangles, it absolutely 100% of the time guarantees them to be congruent. Okay, so that's the main concept that I want to discuss with you, or to have you guys understand. This theorem only works part of the time, and I think it's important to be able to visualize and realize the times that it doesn't work isn't saying that the triangles are going to be incongruent. It just says we don't know. Okay, they could be congruent or they might not be congruent. Okay, so And I do have some other theorems and proofs here that I'd like to go through at some point with you. We're just trying to do it today. Okay. I'm going to open up a section 4.6 about hypotenuse leg. Very straightforward, very simple if you realize we're working in right triangles and identifying whether triangles are congruent or not based off of the hypotenuse being congruent to a hypotenuse and a leg congruent to a leg. The chapter review is open. So you can work on that and you can work on 4.6.